Okay, so here we're going to look at another example of proof by contrapositive. And again, we want to look at an example that does not involve even an odd. And so we're going to prove the following statement. So if m does not divide n times t, then m does not divide n and m does not divide t. Okay, so that's what we want to prove. And we're going to do this by contrapositive. So the first thing we're going to do is to write down the contrapositive. So the contrapositive, and again, it's because the assumption here involves, first of all, not dividing, which is a bit tricky to work with, and also not dividing a product, and then saying something about each of the pieces of the product. Um, so this is it would be difficult to try to do it this way, but the contrapositive is a little bit cleaner. It says if m divides n, the and becomes an or, right? Or m divides t, then m divides n times t. So we're going to prove that statement, right? So, okay, here's the proof. So assume m, n, and t are natural numbers. We want to show that if m does not divide n times t, then m does not divide n and m does not divide t. We will proceed by contrapositive. Hence, we will assume that m divides n or m divides t. Now, again, we can use this without loss of generality here because um, m divides n or m divides t are two different cases, but the way you would prove it is going to be exactly the same. And the way that n and t show up in the conclusion is in a product, which is commutative, so that their roles can be switched automatically. So we'll say without loss of generality, we may assume that m divides n. Again, I just want to emphasize that this is when students use without loss of generality, they typically use it incorrectly. So I do want to introduce this idea to you because you will see professors use this strategy from time to time in class, and you should get comfortable using it at some point because it is an important strategy to simplify our lives. But I want to just again emphasize that students tend to use this incorrectly. And so you just want to be careful. It really needs to be a situation where there are multiple cases, oftentimes two cases, that would be almost exactly the same. And when students mess this up is they have two cases which are similar but not the same, and they do without loss of generality, or sometimes they use it in really bizarre places. But anyway, so we want to assume that m divides n. So by definition, there must exist a k, a natural number, so that n is equal to m times k. Okay, good. So now we want to look at the product, right? So we want to show that the product divides m, right? Then, let's see. So then n times t is equal to m times k times t, which is the same thing as m times kt, where kt is a natural number. So hence, by definition, uh, m divides n times t as desired. So the original statement is true by contrapositive. And we're done. Again, when you have an and in the conclusion, that can be, you have to show both of those things are true. And also we have a not divisible, which is a tricky thing to try to use. And so by using the contrapositive, we made this proof much simpler. In fact, it just kind of falls in our lap. Let's just take a second to think about the without loss of generality here. If you do the other case, meaning that m divides t, then you would have a k that t is equal to m times k. And notice that this step here where we do the calculation would be almost exactly the same because of the commutativity of the product. Um, Almost nothing changes. So that's why we are allowed to use without loss of generality here. But if you're still not so comfortable with that, you can write out both cases and just see how exactly the same, almost exactly the same the cases are, right? And that's why we can do that.